Okay, so when we have a function with a form of a quadratic divided by a quadratic, okay, we can find the horizontal asymptote by dividing every term by x squared. Okay, so what I can do is I can go, okay, I'll divide the x squared by x squared minus 3x divided by x squared plus 2 divided by x squared, and that is all over x squared divided by x squared, okay, plus 3x divided by x squared plus 2 divided by x squared. Alright, now we do the check. Alright, you can see that this is 1 and 1 here, so x squared divided by x squared is 1. Alright, so subtract, and what's 3x divided by x squared? Cancel out an x, that would be 3 on x, and it's plus 2 on x squared. Okay, x squared divided by x squared here is 1, plus 3x divided by x squared, which is 3 on x, plus 2 on x squared. Okay, now I've got it to this form here. I do the check. Right, how does the function behave as the modulus of x approaches infinity? Okay, so as modulus x approaches infinity, you can see this number will get very small, this number will be very small, that's my daughter being a bit loud, this number would become very small, and this number would become very small. So these pretty much become 0. These come 0 as modulus x gets really big. So I'm really left with 1 over 1. So as x approaches infinity, this function is equal to 1. Okay, so therefore I have a horizontal asymptote at y equals 1. Okay, so that's how you get the horizontal asymptote. Right, the vertical asymptote, I've got the function. Okay, now vertical asymptote, let's just rewrite the function. Plus 3x plus 2. Alright, so it's about making the denominator 0. Okay, so what I would do is I'd rewrite this denominator in factored form. I'd factorize the denominator. So factors are 2 that add to 3. That's x plus 2 and x plus 1. So you can see that I have a vertical asymptote. If x is negative 2 here, this denominator becomes 0. So at x equals negative 2. And also at x equals negative 1. So I've got a horizontal asymptote at y equals 1 and vertical asymptotes at x equals negative 2, x equals negative 1. Okay, so if I then want to work out the nature of any stationary points, okay, that means I'm going to have to get the derivative of the function, okay, and get a sign diagram of the derivative. So obviously this function is I'm going to have to use the quotient rule, okay, so it's the derivative of the numerator, which is 2x minus 3, multiplied by the denominator, subtract the derivative of the denominator, which is 2x plus 3, multiplied by the numerator. I'm running out of room here. Quick smart. X squared, what's the numerator? Minus 3x plus 2. And that is all over. Let's just factorize the bottom, which was x plus 2, x plus 1, wasn't it? And remember, the bottom gets squared. So I squared over. Okay, so this is the denominator we're looking at. Let's simplify that. I'm not going to take you through the whole simplifying process. You can do it yourself. It comes to 6x squared minus 12 over x plus 2 squared x plus 1 squared. Okay, so what I do with this, well, I can factorize the top, take out 6 as a common factor, so it's x squared minus 2 on top, and I'm left with x plus 2 squared x plus 1 on the bottom. Alright, now notice this is the difference of two squares, so it's really, instead of x squared minus 2, I can do x plus root 2, x take root 2. Okay, and that is all over x plus 2 all squared, x plus 1 I'm rushing through this one. Sorry about that. Okay, so let's get the sign diagram. Sign diagram for this. Okay, I know I've got critical values at positive root 2, negative root 2. Okay, so let's do that here. That's negative root 2, and let's do that here. It's positive root 2. I also have asymptotes at negative 2 and negative 1. So we'll put that here. Okay. Now you sub in different values in between these critical values to find out whether you get a positive or negative answer into this. And so I sub them in and I get a positive answer, a negative answer, and a positive answer. So functions increasing, increasing, decreasing, decreasing, increasing. So that looks like this. It's increasing this side of the asymptote. It's got a maximum at negative root 2, and it's got a local minimum at root 2. Okay, what's the last thing I need to do? Oh, let's get some intercepts. Okay, x-intercept is when the function is equal to 0. So when f of x is equal to 0, so what's f of x? It's x squared minus 3x plus 2 over x squared plus 3x plus 2 is equal to 0. So you can see that, let's factorize the top factors of 2 that add to negative 3. That's going to be x take 1, x take 2 is equal to 0, because I brought this over here, multiply with 0, so it gets rid of it. So x-intercepts at 1 and 2. Okay, y-intercept happens at f of 0, doesn't it? So f of 0, you can see it's just going to be 2 on 2, which is 1. Okay, so the y-intercept is at y equals 1. Alright, so I've got the x-intercepts, the y-intercepts. I actually haven't for the stationary points. I need to remember, you need to sub this into the original function to get the y value of this maximum, and sub this into the original function to get the y value of this minimum. I haven't done that, but we will get to it. Alright, I've actually run out of paper. Hang on. Where's some paper? Here we go. So, I've got the asymptotes, I've got the stationary points, I've got the intercepts. Okay, so let's say I want to draw this up. Let's just do a mock axis nice and quickly. Alright, let's use what we know. I know there's a vertical asymptote at x equals negative 2. Alright, so let's say that's negative 2. So that's at x equals negative 2. I know there's another one at x equals negative 1. So let's put that one here. X equals negative 1. What else do I know? I know that there's a horizontal asymptote at y equals 1, which we worked out. So that's at y equals 1. Okay. I know that the graph, what did I find? The intercepts are at 1 and 2, so crosses there, crosses there. Okay. I know that there was a minimum at, what was it? Root 2, and if I subbed root 2 in, I subbed root 2 into the function, I got an answer of negative 0.03, so the minimum's somewhere here. Okay, and I know that there was a maximum at negative root 2. Okay, and if I sub that into the function, I got an answer of negative 33. So negative root 2, negative 33. Let's just make out it's here. Okay, because I'm not going to be able to fit it on the screen. Okay, it'd be right. So that would be a maximum, and a minimum. So here's what the graph does. I know it was increasing that side of the asymptotes. Okay, I know this is a maximum, and it doesn't touch the asymptotes. So it's going to do something like that. Okay. I know that it doesn't touch this asymptote. This is a minimum. It's going to go. Now, watch this. I'm going to tell you it crosses at 1 because we found the y-intercept to be 1. Okay. And look, it's actually crossing the asymptote. Here's an interesting little thing. I'm going to show you. How do I know when a graph crosses a horizontal asymptote? Because a rational function can cross a horizontal asymptote. If I know the asymptote is at y equals 1, what I do is I take the original function. So I take the original function. Oh, that's a plus there, wasn't it? And I make it equal to the equation of the asymptote. What was the equation? Y equals 1. So I make it equal to the equation of the asymptote. Now watch this. If I rearrange this here, I get x3 plus 2 is equal to, bring that up there, multiply it by 1. So it's, okay? Collect like terms, that's going to give me, the x squareds cancel out, it's going to give me 6x is equal to 0, okay? And x equals 0. Okay, so what that shows you is this, that this graph crosses this asymptote at x equals 0. So the x equals 0 is where it crosses the asymptote at the y-intercept there. That's just a little nifty thing to know.